Hi there, welcome. This is Mrs. Baxley, and I'm going to try and help you understand the activity series worksheet a little bit better and the most important information I'd like you to get from it. First, I want us to look at letter F on that worksheet, and I'm going to give you a real-life example of what's happening in this particular reaction. Now, you'll notice that it's showing copper 2+ ions in this solution, and it's showing an aluminum strip inside this beaker. Now, in real life, the copper doesn't exist by itself, the copper ions. It's formed because of a copper salt that dissolved. So this could be copper chloride, in which case you would also have chloride ions in the beaker. Or it could be copper nitrate, in which you would have nitrate ions in the beaker. Or it could have another anion. And the interesting thing with this is these anions are not part of the reaction. So they're called spectator ions. So the very first question in here is the most confusing question in the entire worksheet. But what they're asking is, could sodium have reacted with copper? So could there be sodium ions in this beaker as well as copper ions? Well, sodium cannot combine with copper. So when it dissociates, you could not have sodium ions that came from a compound with copper. But you could have nitrate ions that came from a compound with copper. So the answer to the first question is that it is possible that you had nitrate ions as spectator ions, but you could not have had sodium ions as spectator ions. Now, the next thing I want us to consider is, in real life, what would really happen if we put a strip of aluminum in a copper chloride solution? So we have copper ions and chloride ions in the solution. And as you watch, we actually tried this in class. If you notice in example number F in our packet, this is the exact depiction of our reactants. We have the copper chloride solution, copper 2+, and with the aluminum strip that we're going to put inside that copper solution. We actually use copper chloride, so there are some chloride ions in there as well, but those are not part of the reaction. Those are spectator ions. Little thing. So if I take the copper, and into the copper, we're going to place the aluminum. And you can gather around and look and see that we are producing some bubbles.
Whoa.
And very quickly, you'll see the aluminum is changing color.
Huh? Wow.
What's happening in here?
It's going black.
It's like there's a thin copper coating forming as the aluminum, which is more reactive than the copper gives up its electrons to the copper.
Gosh.
Excellent, John, that's right.
Now they're aluminum
So
ions.
the copper,
It's smoking.
the copper is replacing the aluminum. The copper is coming out of solution, and the aluminum is dissolving into solution. You can tell it's smoking. That is an extremely exothermic reaction, giving off a good bit of heat.
Nice.
And you can see it happens pretty quickly. So the interesting thing we see here is that the aluminum, which was a neutral atom, and the copper, which was a 2+ ion, have changed electrons. So where did the electrons go from, and where did they go to?
Some of it at the bottom.
From the aluminum to the copper.
And it's
Yes.
like murky at
The,
the
the copper now is neutral, so it gained 2 electrons. The aluminum now is dissolved in solution, so we now have
There's
aluminum
like a
3+
murky
ions.
white like around the top.
Yeah, and like
I
the
guess
bottom
it's
is
a
kind of.
It's some of the aluminum that's not
Oh, it's
totally
solid
dissolved.
smoke.
I can see if you trunks.
Very nice. All right, go ahead and pause the
Thanks,
video. So, and what we just saw happen, we had a piece of aluminum in a copper solution. I know this is a different one here. And what happened then is the copper came out of solution as atoms, and then the aluminum dissolved in the solution as aluminum ions. Now let's look at, this is example A on the same worksheet. And this is a similar thing but with different compounds or different substances. All right? So we have a magnesium strip in a zinc solution. This could be zinc chloride, it could be zinc nitrate. It doesn't matter what the anions are because they don't change between one thing and the other. All right? If we put the magnesium in the zinc, what happens here is the zinc replaces the magnesium. So what I want you to notice with this is we can write two half reactions. The first half reaction is the magnesium that is a solid turns into magnesium ions dissolved in the water. So it's aqueous. But this isn't balanced charges. What do we need to do to balance these charges?
Add the zinc with charge to one side and the pure zinc to the other side.
Well, that's going to be our second half reaction. With this half reaction, to balance the charges, we can just use electrons. So where are we going to put electrons?
On the right,
And how many?
2.
That's now balanced, right? We have one magnesium on the left, one on the right. These charges balance to 0, that charge is 0. That's one half
2
reaction.
plus negative 2%.
Is this oxidation or is this reduction?
That is oxidation.
Oxidation. Losing electrons is oxidation. Or if the oxidation number goes up, that's oxidation. Or if the electrons are on the right, that's oxidation. Now, we're going to use our other half reaction. The zinc started as an ion, and it turned into solid zinc. Now, where can we put electrons to balance this? Left side. How many?
2. Strong
Okay.
side.
Plus 2 electrons on the left. Now, is this oxidation or reduction? Okay. Process of elimination, it has to be reduction. But also you see that it gains electrons, so it's reduction. Or the oxidation number goes down, so it's reduction, it's reduced. Or the electrons are on the left. So what we can do to get the complete net ionic equation is we can add these two together. So if we put solid magnesium and we put it into a solution of zinc ions, the electrons cancel out on both sides. So we now have magnesium ions in solution plus solid zinc coming out of solution. All right? This is called a net ionic equation. If we had used the entire equation, suppose we use zinc chloride for this, then our complete reaction would include the chloride ions but these are dissolved. And the chloride ions on the reactant side are the same as the chloride ions on the product side. They didn't change. So we typically just leave the net ionic equation, and that's what we're going to be looking for here. All right? So I want to do one more thing real quick. Let's look at the second reaction, where we have magnesium in an aluminum solution. And we are going to write the two half reactions for this, and then we're going to balance them. And these are the steps when you're going to do this, okay? To get a net ionic equation, we're going to write the two half reactions. Then we have to balance the charges. Then we have to balance the atoms. And typically, when we balance the charges, that will automatically balance the atoms for us. But let's look at this particular example here. So if we write the two half reactions, what's our first half reaction?
Turns into magnesium 2 plus 2 electrons.
Yeah, what John said.
Is that oxidation or reduction?
That is oxidation.
There you go.
Because it goes up.
It goes from 0 to 2 plus.
Very good. So our next half reaction,
It would be aluminum 3 plus. Yields
Yield,
Al plus minus
minus
Where do the electrons go?
Plus.
Left or
plus
right?
on the left.
On the left.
How many?
3.
There you go.
Oh my god, we got 'em good.
So that balances out.
Never
And
been
this
seen.
is a solid.
Yes.
These are our two half reactions. So this one is a reduction reaction.
That just happened.
Now we've got a problem. If we combine these two reactions, our charges do not balance. We have 3 electrons on their left and 2 on the right. So what can we do to balance the charges?
That was a ratio of the magnesium per 2 aluminum.
Okay, so we're going to multiply everything up here times 3. Okay, so we're going to put a 3 here, and a 3 here, which will turn this into a 6. And then what are we going to do the aluminum then?
2.
2.
2.
That makes 6 and 2. Now our charges will balance left and right, 6 on each side. So now our net ionic equation for this reaction, we're going to put everything on the left side, including our new coefficients to balance it. My 6 electrons on the left balances 6 electrons on the right, so I can omit those. I've got 3 magnesium ions and 2 aluminum atoms. Do our charges balance? Plus 6 here, plus 6 here, good. 3 magnesiums here, 3 magnesiums here, 2 aluminums here, 2 aluminums here. We balanced it using 2 half reactions. This is the main information I want you to get from this packet. By completing the rest of the packet, it'll just reinforce all these concepts. I'd like you to complete the packet, except you don't have to do the very last problem where they're doing the anions. All right. If you've already completed the packet, I'll post the answers so you can check your answers. But hopefully this will help you understand a little bit about what this packet means. This is what I want you to understand for the most part from this packet. Also, though, you all are going to understand the activity series. If something is more reactive, it wants to ionize. So the metal that ionizes is more reactive than the thing that drops out of the solution as a solid. Okay? Very good. You can stop that.
Bam.
Thank you.